And I really, thank you very much. Thank you very much, everybody, for joining. It's really a pleasure for me to be in touch with the Capital District engineering community, and especially those related to electricity, which is and energy. So today I would like to give you a little bit of an overview of work that I've been doing for almost 10 years on grid modeling. And what's special about this is how we can make models portable and interoperable, and being able to deploy them from your computer using Windows, Linux, or Mac, or to the cloud. And this is all possible thanks to the power of open access standards that have been successful in the automotive and aerospace industry that I am adopting here. So you can see here some little diagrams, and you can see a picture of a little dog, and I'll tell you all about it in a few minutes as we go along. Okay, let me just turn on the laser pointer, and there we go. So why do we need modeling and simulation in general terms is going to be the main motivation, but also in New York State, we have future grid needs. And if we don't evolve in the status quo, what are going to be the consequences? And how can I make these predictions? The reason is that it has already happened in other places. So we have some evidence of why we need to adopt a more efficient and interoperable process. I will tell you the story about Modelica, which is an object-oriented, equation-based, open access modeling language. It's not a software tool, but as a computer language that allows both the human and the computer to understand physics-based models. And I will tell you about the FMI standard, which is another standard from the Modelica community for model portability. And finally, I will show you how we model the power grid. As in this example, we have the WECC PV plant model implemented, and we can do it in this language. And we do that with our library, which is called OpenIPSL, and has this little dog as a logo. There's a joke there soon, okay? So that's the discussion of the specific example that we're going to talk about is the PV, wind, battery, and BES models that normally, if you're in utilities or as a consultant, you have to use in the Eastern interconnection of the US, you have to use Siemens PTI. So to give you proof that this is a viable approach, that we can get the same and better results than this, the state-of-the-art tools, we actually have a process for model verification and software-to-software comparison. I'll talk to you about that. And finally, portability and interoperability through the FMI standard will show you how we can go from the computers, but we can also actually even deploy it in real-time simulators or in the cloud. So that's the idea. And I'm summarizing here many different projects where we have developed these results. So I didn't put a specific thank you, but there's many people that has been involved. So why do we need models, and why do we need to do simulations of the grid? So we have been doing this for a while now. Originally, these were circuit models with transit network analyzers that will represent the equivalent system, or we have equations. But when it comes to power system analysis, we actually need to study how each device and how devices among each other behave when they're all together, not in isolation. Okay, so as new devices come along, we need to perform these studies, and most of you, a lot of you are probably aware of that. Now, if you look at the evolution of power networks over time, the one thing that has continued to increase is network size and So we connect more things together across a broad geographical space and the complexity of the devices. So an electrical generator, it is fairly complex piece of engineering, but the ones that we're adding now, like inverters, they're different in the complexity in the way that now you have a piece of software that is deciding how physics should behave. And those things are contradictory sometimes, okay? So in the past, what we have been doing is that we adapt the existing tools to deal with these issues. Now, the reality of things is that the approach should help us to anticipate, to be able to look ahead and be able to foresee failures and give us an understanding of how to mitigate those failures before they occur. Now, the reality is that we have the status quo that we have has failed. And every time that we fail to anticipate, it results in tremendous costs. The most famous example is the impact of this Northeast blackout. I mean, that was very complicated. Even I don't think it was even possible to simulate the time that it happened and after one. But the reality is that we keep hearing about issues related to system operation, and the existing model and simulation methods and associated tools are unable really to help us fully describe behavior and do it efficiently and quickly. Okay, so why am I concerned about this? Because we have a future energy scenario. We are adding these gigantic amounts of renewable energy sources, especially in New York State. At the bottom of Long Island, we have all of this wind turbines coming along. And at the lower scale, we have PV panels at the residential level and also a utility scale PV coming along. Now, we are going to need new modeling and simulation capabilities. We can't just stay where we are. The reason is that the performance of these clean energy technologies needs to be studied and before it's deployed, so you don't get nasty surprises. And the models that you use to do this kind of studies should be portable, so we can use it in different environments to perform different types of analysis, and more importantly, to support decision making, which is at the end what matters the most. So the challenges that we have is that today we have locking. So we have few specific and proprietary software tools that bound the models inside of the tool. So that's not just your data that is very hard to get in and re-implement in another tool, but the equations of the models are interleaved with a specific numerical solver. So you actually, it's almost impossible to move them outside and get the same answer without full re-implementation. Okay, lack of interoperability in that sense is not just that it's hard to move parameters around and descriptions of the network, but you don't really have a model unless you have the exact equations and how they are implemented to be able to get the same answer. And this leads to duplication and inconsistency. So many models are created and represent the system in different platforms, and it's extremely difficult to get the same results between two tools. The current situation, for example, when we were working on NIPA, most of their work for planning models is done using PSSC. However, they have a real-time digital simulator called from OpenIPSL that when you build the models and you compare them to each other, they're nowhere near. And this is not a problem really of the tools per se, but the fact of how we have been building this for years without really understanding the consequences of what is it going to affect us in our capability to do things. So what can happen if we don't, if we just keep continuing doing what we do? First is that we will be unable to understand the dynamic performance and interaction with the grid of the new technologies, and we will have unexpected and costly consequences. This will lead for sure for major design flaws. And that will really slow down the adoption of clean energy technologies and ultimately increase their cost. Because if we have problems, then there's going to be more questions. It's going to slow down the process to get them interconnected. The best example is to look at Germany for this. In 2011, they started a costly retrofit in the paper that I'm citing. It was $175 million to retrofit 350,000 PVs to address issues with over frequency protections. I mean, in a lot of the models that are used for dynamics, those are not even model. So the impact was not studied for this case until it was too late. So you can imagine that it's not just a question of cost or retrofitting, but the logistical nightmare for 350,000 PVs to be properly retrofitted on the software level on the firmware. The other example that I have for you is a topic that I worked since 2011 with, that is controller interactions between wind turbines and the grid. In the old days, this is similar to subsynchronous control interactions, but now you can get it subsynchronous below 60 hertz and supersynchronous about 60 hertz. And the problem specifically in this case study that you can find this book chapter that we did is that the control interactions were not identified until you got problems reported by customers. So this was about 13 hertz, this one. And they, of course, that was kind of visible through flicker. So now the problem is to get rid of it, you have to ramp down the wind turbine. And if you ramp down the wind turbine, there's only our great friend gas or coal. Well, only gas really that can speed up to catch up to that. So it will create more operational costs if you want to get rid of these nasty resonances. Wherever there is a resonance or a control interaction, it's bad news. And we've seen similar problems in with PV. So these are just two examples. Okay, the other caveat is that the current process is time consuming and expensive, especially when it comes to develop models for new technology like PV and wind and in multiple tools. This is a report from the Australian electricity market operator, I think, from 2017. And they show that for one new type of device, right, new type of wind turbine, new type of battery energy storage system, the cost of development for a new model can go up. Is it in the graph here? Sorry, for the graph here, new synchronous, asynchronous models unavailable. It can go around $600,000 for one model in one tool. This is a tremendous cost and is time consuming. So the lack of interoperability will only increase the cost for porting and analysis and verification. It's a terribly slow process. So the other problem of the lack of interoperability is that if you are familiar with this picture, this is the Tower of Babel. And this is the situation that we have between different domain specialists. So somebody that does studies of electromagnetic transients, they sometimes don't understand the people doing other types of studies. And this comes with this sort of narrowness of the specific domain tools. So it creates a difficult to understand requirements from the bottom up or from the top down. So if you look at power electronic systems, we assume that they can do everything we want to and they're fast, but all of the cost comes in heat, and heat can lead to fires. So you see a lot of PV converters catching fire because we're asking them to do things that they were not designed for, because the interaction between system level specifications and design at the lower level, there's not good communication. And models are our only way to communicate technical specifications other than, well, standards. Now, the proposed solution is to use open access. That means no paywall. That means I'm not going to have to pay the IEEE for $5,000 for a PDF where all of the utilities participated in the development of it. Same thing with UL, same thing with IEC. Having open access standards will give us the speed of development equivalent to the one of the internet. The internet was built in open access standards that not only define the documentation of how to do the implementation, but also sometimes have open source to do the implementation, open source software to do the implementation. So the standard is developed and maintained by a community, also in an open form. So you can actually go online and look at the standard development for this and see all of the comments in Git, and people has to discuss openly. So that really helps. The other aspect of this, that this is both computer and human readable modeling language. So it's not a programming language only, but it's to model physical and cyber physical systems. And the key here is that by having a language where you can define all of the equations in their text, in the textbook form, makes a clear separation between what the models describe on the physics and the software implementation. So there's a clear demarcation, and there's never a question, what is the correct model? The correct model is always the equations. And it allows competition between tool vendors then, because it's usually a problem of the tool and not reality of the model. So we create a very natural separation through this power, and this will avoid vendor locking and increase competition. It will avoid vendor locking because, as I will show you, I can run my models on 4 different tools without touching them, just loading it up in another tool and running them. That's extremely powerful because we can use different tools for different purposes, but also we will force competition as users on the vendors of software. So that's why I think this is like Superman to the rescue in a way. Okay, so let me tell you about Modelica in power systems. I will not go into a long description of Modelica because we'll need a whole hour for that. But let me tell you a little bit about history. So the Modelica language actually was established first in 1996. So it's really now a mature language standard. And it was around the 2000s that we saw the first attempt by Weissman and Bachmann to do electromagnetic modeling. So Bachmann and Weissman were in ABB in Switzerland, and they started using it for electromagnetic modeling. And this resulted in the first commercial library called SPOT. And it's closed relative open source that is called Power Systems in 2014. The issue with this is that it takes advantage of all the powerful features of the language, which means that you can do everything with it, which is hard for people to understand in some cases. So if we take a step back on the level of detail of modeling, there has been libraries being developed, including mine, for electromechanical modeling, or the so-called transient stability analysis. And this neglects fast dynamics, although I can show you how we can interface it with, not interfaces, but combine them with electromagnetical transits anyway in the same environment. But normally this is the highest level of detail, okay? So the first one to do this attempt was a library called ObjectStan by Mats Larsson from ABB Corporate Research. And then Winkler updated that in 2015 and adopted this dynamic modeling. Then in the Pegase EU project in 2011, they developed a small library, which I used during my time in Sweden as the basis for the iTesla library, IPSL. And after 2016, since there was no more project funding, I went on my own with my students. Well, it was actually the students that will be the evolution of the next generation of the library, try to be built in the open source approach. So that's the OpenIPSL library is basically what we will use to represent the power system models, and Modelica will be the language. So as I mentioned, has no paywall. And when you get the link of the presentation, I think we can put it in the chat later. You will see where to find the language specification and everything related. There's also a standard library of thousands of models that allow you to do multi-domain modeling. So here you see the tool that I use called Dymola. And in all of the Modelica tools, so if I shoot up another one, well, I might not have it in, yeah, it's right there. So if I shoot up another one, I can show you how in the same tool, you have the same models to do multi-domain modeling. So you can model the thermofluidics, mechanics, like multi-body system simulations, and so on. So the language provides, so the Modelica Association provides this library with thousands of models already. So let me just show you that really quickly. This is another tool from another vendor called Warframe System Modeler. And if you see here, there is the same Modelica standard library that standardizes all of these representations. So for example, if you want to build some simple electrical circuits, you can do so in this environment. You can do digital circuits and whatever you like. So that's for typical circuit analysis. My library, on the other hand, is dedicated exclusively for power systems. So right now, there's 9 tools that support natively the Modelica language, and one of them is open source called OpenModelica. And there is a vast number of open source and commercial libraries. So OpenIPSL is open source. You can find it online at openipsl.org. And it contains a vast number of power system components for time domain modeling and simulation. So basically similar to what PSSC does. And they have been verified against PSSC and an open source tool called PSAT. So what you can do with OpenIPSL is you can have an ambiguous model exchange. You can use it in different Modelica tools, and you can export the models to other environments that don't support the Modelica language. You can export the models using the FMI standard. And it provides, then we have a formal description of the models, which I will show you in a second. So they are not only possible to use with one integration method, but you can use 10 of them. And using Dymola is as fast as PSSC, as a study that I collaborated with the developers of Dymola for some models that I have available. Okay, so the reason to develop another library, as you saw, we have there was a number of libraries available. It was really the key one for me was the resistance to change. So resistance to change is defined as an irrational and dysfunctional reaction of users and sometimes software developers. Okay, in the power system domain, we are very skeptical about tools that are different to the ones that we have used or developed. And therefore, we are averse to new technologies. This is what you call your baby is ugly syndrome. Okay. So the only way to address it is to have change agents that will contribute positively to address resistance to change through actions and interactions. So the strategy is that we don't tell you what software tool to use. We tell you, here is the library, here's 9 tools for you to choose. Pick the one that you want. The job then is on us to be able to support all of those tools because they might have some problems with our models. We propose then that you have an unambiguous exchange of the models, which means that you can move it between tools, and that's for free using the Modelica language, but that's the way that I can sell it, let's say. We can decrease avoidance forces by showing people that I can give you the same result as the domain-specific tools, and that accuracy is more important with today's computers than performance. So I can actually show you with my tool that I can make my models more accurate by using a a better solver, a better numerical integrator, such a multi-time step error correcting solver like DASL that is used in other domains. And this is really my long-term effort to bridge the gap between the people in the Modelica community that, Bosch, BMW, Mercedes, they all use this stuff, but it's not used by the electrical community. So that's kind of my work. I work pro bono, right? I'm part of the Modelica Association, so that's part of what I like to do is my third duty. So if you're ever familiar with PSSC models, you will recognize the famous GenROE or GenRU or GenSal. And if you look inside of my model, you can see the equations that we had to re-implement from scratch, looking at the PSSC documentation and all papers from the 1970s. Okay, so you can type the equations directly, or you can use a block diagram. Inside of the block diagram, each of these components at the end has the equations that you can see. And since we're doing this remotely, it's very easy to grab my machine and go and show you an example really as quickly as I can, right? So here is a single machine infinite bus that we use for teaching. But if you see this little guy, right, if we look inside of it, it has a machine of order 4. Let me instead show you the PSSC machines, which is what most people are interested in anyway. So anyway, you can see here GenSal. All right, and we see in the text layer, this is just the carrying parameters and so on. But here you have the equations. And if you look at the mathematical notation, it will convert it for me. And this is the equations like we have in the textbook. So you have here the differential equations for the voltage behind the transient reactances and the fluxes. There is a use of the object orientation also. So you're not seeing the swing equations, because all the models use the swing equation. So object orientation, we type once, we use everywhere. So you can see the base machine has actually the differential equations that we use for the swing, which I am failing to see in this moment because of demo effect. But let me go like that. I'm going to find it quicker. Yeah, so yes, here at the bottom is the derivative of speed and derivative of angle of the generator. I mean, this is simple for me to read, as you can see. So that's the language. And this little library shows you all of these components, and you can assemble a variety of type of power system models with it. So let me go back to the slides. Of course, I can run a simulation if you're interested, but this is the idea, right? So we can use and assemble our models here. Okay, there are many applications examples with the library if you want to try it. There's this textbooks examples like the Klein Rogers Kunder 2 area for machine system, IEEE test networks. This is a distribution network from Norway, so it's the actual network. And I will show you something more soon. Okay. So what is the new developments that we're doing are focusing on implementing this WECC type of models for renewable energy resources. So our library has to follow what is being done by the community. So even though I can make models that cover the entire timescales and so ultra fast to slow, I can do that in Modelica. I am trying to reproduce and show that we can do the same thing here so they can be adopted, right? So the library will cover basically subsynchronous resonance, transformer energization, transient stability, small signal stability, voltage stability, and every type of analysis that you typically do with those tools. So based on the guidelines that we have published by the WCC, we implemented this model. So this is the picture that is exactly the same as the block diagrams that we have in PSSC. So there is a converter model. It can be, it's the inverter usually. Then you have this current limit logic, which is basically a way to model the maximum current limits that are going through the electronic circuit. And then you have, so this is really an abstraction. There is very little physics, more than a few time constants there, and some limitations. It's not like you're modeling the transistors. Although you can do it in Modelica, this is not what we do, not what is done in typical grid analysis, right? And then you have what is called the upper level controls in power electronics literature, or we call it just controllers for P and Q control, or the plant level controller. So these modules, the yellow one is the plant controller, the blue one is the different modules, and finally the generator model. So how do we build those? We use the Modelica standard library for everything we can. And if there's something that that behaves different in PSSC, we have to re-implement it from scratch. So we actually have to make a tiny little model in PSSC and try to figure out what the integrators were doing for that specific model. That's a lot of sort of clean room engineering that we have to do, but we can implement this using the specialized blocks in our library. And finally, we have an electrical interface that connects the phasors, voltage, and currents together through this electrical interface. So you could see in my little model that we had before over here, that this electrical interface, it's at each, as I connect every component together. If you go and look inside of the transformer, you have one pin on every side. And if you look at this electrical interface and you look at the text, echo, you see here that I only have the voltage and currents in real and imaginary form, which give us a phasor in 60 hertz frequency. So this allows me to just attach them to each other. And it's not my problem to figure out how the current is flowing. It's the problem of the tool later on. Okay, so let me just take one step back. I'll show you this in a second. All right, so that's how we build those models. Here is an example of the implementation for the converter. So as you see, we reutilize a lot of the Modelica standard library blocks, and then we have to develop our own implementation of the low voltage protection logic, of the low voltage active current management logic over here. And we basically combine using the block diagrams for models that already have a block diagram definition, remembering that behind those block diagram definitions, there is always equations. So the equations are never hidden from the user in principle. Okay, it could be that you have some sort of a proprietary library that uses encryption and you cannot see it. But if you look at a simple PI controller, you have here the actual equations of that model. So it's never hidden, which gives you transparency and helps in understanding, right? Okay, so in this case, we combine both modeling at the textual layer, like normal programming, and the graphical object-oriented modeling. And we use object orientation throughout. These models are made by committee, and you can tell that because it has all these switches on a num to decide which function to enable depending on the manufacturer. So we enable the same approach using logical switch blocks. So now you have an entire module for the PV controller, and you have the current limiting logic over here. So we are basically building step by step all of this. This is for the PV controller. Similarly, here is for the battery energy system controller. And similarly, here we have for the plant level controller. I know I'm skipping a lot of details, but I'm trying to leave time for questions. But in any case, we start from the document, we go and implement, and then we have to compare against PSSC. This student was Brazilian, Fernando Faquina did this. He suffered a lot, but now he doesn't want to use anything else because he's very capable and fast. Okay, so how do we provide initial conditions for our models? Well, we're working with a language that is not just for power flow, it's for dynamics. So when you're trying to solve a numerical problem, you need to provide a starting guess. Usually, power system tools receive a power flow take the power flow and solve some initial equations. Well, I am a tricky guy. So when you look at our models, we can take an initial condition value. So if you go here and you look at the machines, and let's look at Gensal, I get an initial guess based on a steady state. You can guess a steady state, or you can read it from our power flow, as I will show you, and then try to calculate all of the initial values for the states. So here you see that delta zero, the initial angle of the synchronous machine, is pre-calculated as a parameter, and is somewhere around here. It's in the base class because all of them use the angle of the machine because they're all machines. So I cannot locate it so quickly right now, but it's here somewhere. So I'll just continue. So that's what we do. So we need to have a starting guess. Normally you will use a flat start, but that's not very good. So what we are doing is that we are trying to solve a power flow and linking that to our model. And we use a different Python-based tool to do that. Okay. And based on that, our models internally calculate their own initial states, and then they provide that to the Modelica tool. Now, the Modelica tool will solve an initialization problem that includes all of differential equations and the algebraic states. So it has to be a valid equilibrium for the dynamic system and not just a power flow solution. Power flow solutions can be invalid physically when you take into account the dynamics. Okay, so we just need some guess values. So just to show you a clear example of how those guess values look like, let me go here into my Nordic 44. There's a Nordic grid model. And if you look inside of this guy, right, that's the plant. And inside of the plant, you have all of the controllers. And here, you're basically passing the power flow data in this case, and you're passing it from a higher level. So we're actually solving a power flow solution and then passing it along this, like most tools work. And I can talk with more detail about that if you have some questions later. Okay, so how do we propagate this initial condition from the bottom of the model to the top? It's by inherence. So it's very simple with object orientation to say, hey, this parameter that is inside that is going to be used in here, it has a start value, and the name is going to be IQ0. And then from the top level of the model, we already know that that's going to be required by the internally. So we will calculate this IPQ0 and IQD0, which are the D and Q axis, if you want to think about it, for this state. We calculate them through equations based on the initial data we have. And the equations, if you look inside, are basically, here we're calculating the current from the power and the voltage, just like in the textbooks, exactly the same. Okay, so that's very beautiful. It's a transparency through the process, right? Okay, so now that we have all the pieces together, how do we simulate these things? So we take the controller of the PV source, the module to represent the PV inverter, and we connect it to the grid. We give the dispatch values, the reference power and reactive power, and we give it the steady state. And then we will test all of the control modes possible. Now, these models have this bunch of flags depending on what you want to use, and the user just has to click on the screen and select from our model which conditions and which flags have to be enabled. Okay, so inside of the same model, we can have all of the representations required. The validation process then, when we have the system model put together, is we need to verify. So we will run a simulation with PSSC. We will run a simulation with my Modelica tools, and then we will compare. So the type of
Luigi, I think we lost your audio. Can't hear you.
I don't think he can hear us either.
Okay. Can you hear me now?
No,
I
oh,
changed the
we're
microphone.
back. Yes.
Yep. Yes.
Great.
Now we're good.
So I was here showing you how we validate or work. So let me take one step back. This model implemented in Modelica tool and replica in PSSC, run the same scenario and do and compare. So here you go. So here we have the evaluation test for the when we use both these two modules, RegCA and ReEECB, the ones that we had before, right? A and B for the inverter. And what you see here is that PSSC and OpenIPSL, my library, will give you exactly the same result, except during some points on the fault, which is just a numerical simulator problem in terms of the numerical method. So there is one point that is a little bit off exactly during the fault. And that's because I haven't been able to revert engineer how PSSC actually applies the faults. But this is a one-to-one match if you look at the dynamic performance when we do these experiments. So this is what we calculate is the root mean square error across simulation. And this is below the numerical accuracy of 10 to the minus 3. So we have 10 to the minus 5 and 10 to the minus 4. Most of the errors are during this instance of the fault, really, and they're basically garbage, numerical garbage. Here is another example. We have the reactive power controller, a voltage reactive power control for the BES. So plant level reactive power control, local level voltage and reactive power control for the battery energy system. And you can see the error here for the P and the Q for both cases. So again, the same behavior applies. Or mismatch error only occurs where we can't really figure out what is happening now. But you know, it's very good when you look at the root mean square error as a metric for validity. Now that we have a model and we can do things just as PSSC, we can do more. So one thing that you cannot use PSSC for because it takes forever is to give it an irradiance table of 24 hours and simulate a sub-second level dynamics. So you can apply this irradiance table and let the simulation run and see the dynamic effect on the system, all the way from that input of irradiance to the output. Similarly, we can do the same for wind, and we can do all of these things that are not possible to do because you will have to wait forever with PSSC. But here we can use the Dazzle solver that has that is not a fixed time step solver, but it's an adaptive time step solver. So it can run very quickly unless there's something weird happening and I will have to iterate faster. So it adapts the time step to maintain accuracy. So now we can do more things, right? We can do stochastic modeling combined with deterministic simulation models in one. All right, so that is the last part of the presentation. So now that you have a nice library, Luigi, and you can move models around, what can you do? Well, we can take advantage of these portable and interoperable models with open standards. So we can use the object orientation, right, to parameterize our models. So for example, we actually take the results from PSSC or from a tool called GridGo and parameterize our models directly. We can use many tools to run those simulations, and we can use the FMI standard. That is a standard that is now supported by more than 136 tools. So the most popular tools for engineering, not just power engineering, but engineering as a whole, they all have support for it now. Power system tools, only EMTPRV so far because EDF forced them. Okay. The other thing is that all these models are public. So in my case, you can use them for whatever you want. I'm not gonna chase you around. The methods is to leverage that we have implemented the models with these open access standards and be able to create this repository. So that's the idea to how to support interoperability. So what is this FMI standard? This FMI standard is, again, an open access standard from the Modelica Association. And what it does is that defines a container and an interface to exchange dynamic models. And it combines XML files that describe the model, binaries, so executables, or the C source code itself into a single zip file with a standardized interface. Okay, so I have to speed up, but as I said, this would allow you to do co-simulation by running the model with its own solver and the simulation tool that supports it, or integrated with the model itself. So the first thing to show you is the performance of these models in different Modelica tools. So this is the same model running in Model on Sympact software and Dassault's Daimola software. And you can see we get the same answer from 2 tools. That's unheard of in power systems, but not only 2, I give you 4. We are able to do it on Medit and Wolfram system model. And what that required from us was a lot of hard work and to be able to be very methodical and disciplined on respecting the Modelica language standard. So some tools will let you get away with being a little bit dirty when you're doing things. If you want interoperability, comes at the cost of discipline. So we learned that the hard way in the latest version of the library. Then if you want to run them with the FMI standard, here's a little example where we take the entire model of the Nordic grid that I'm showing in the back, and we put it inside of Simulink only by using model exchange. So we can use all the MATLAB features that people likes to use. You can do the same thing with Python. You can do the same thing with 136 tools, basically. So this allows you to model a whole system or just a piece of it. So when you're trying to deal with the whole system, it's better just in Modelica tools. They're more efficient, but you can still do it if you need to. Well, one of the extremely good luck that I've had in my life is that there is only one real-time simulator that supports this standard, and luckily is DSpace through Scalexio. So you can actually generate this FMU that includes the C source code. You can give it to the Scalexio real-time hardware, and you can run the model in real time. So you don't need to re-implement everything to use a real-time simulator. So we don't have to do anything that loaded it in the software environment of loading this FMU container into the software environment, and then, you know, putting wires to couple everything together. And here is the proof of concept. This is the model that we were running. We were actually trying to design how to inject an external signal to be able to generate enough dynamic content to identify damping and frequencies of oscillation. So this was done with that in mind. So you can do very, very nice and advanced things with, you know, all the way from offline to real time. So this is just a picture. I will avoid it. Finally, the cloud. So this is a project that is ongoing with Dominion Energy. The main challenge is, so if you look at this spectrogram over here, this tells you time, and this tells you frequency. This is for an entire day. And you can see how you have a high frequency, well, relatively high for power systems of about 17 hertz. And then you have another frequency here that was completely shutting down. We identified that this was a power plant that was ramping down, and this was actually a solar plant. So we can actually see the dynamics and how they're affecting the system. The problem is that all of their measurement stuff, it's in a cloud service. And all of the models are somewhere else in a computer, and they only run on Windows. And we can't integrate them together without having to pay a fortune. So the idea is that instead of having to bring all the measurements down, do everything locally in the machine, why don't we just put the models in the cloud also, now that we have this? So the idea is to deploy them in this predictive grid platform and give engineers tools to calibrate their models that we have implemented for plants. And then you calibrate it there, find the new parameters, and put them back into the PSSC model, or do more advanced things like doing estimation of unmeasured variables. So the Dominion is the utility. They don't own all of the PV stations, but we could actually use an estimator to look inside of the controller of the PV to see what it's doing. So that's one of the ideas. So we basically create the models, as I showed you before, export them as an FMU, and calibrate them. Here are the steps that we do to couple the measurements, the model, and the optimization routine to do the calibration process via optimization. So just to show you here, here in the corner, you see here, there I'm telling which parameters I want to calibrate, which is the exciter gain and time constant. And there we're estimating the steady state, because the steady state doesn't exist when you have measurements. So we're trying to estimate an equilibrium to start the simulation from. And over here, you can see the optimization method used is a genetic algorithm with a conjugate gradient integrator. And you can see here how we're trying to, how the error between the model and the measurements is decreasing. So I'm just going fast. So our models, you know, even though PSSC and Modelica give you the same answer, it doesn't reflect reality. And it was only through doing this whole exercise that the engineers stopped trusting the PSSC model, because we show them we can give you the same answer as the simulation model, but doesn't match reality. So now we're trying to improve this model so that it can actually capture reality at one of these stations. Okay, so we're hoping to release Q2 the next generation of OpenIPSL. We released a beta of version 2020 in December, and we're hoping to release version 2.1 that includes all of these renewable generation models by Q2, so hopefully before the end of the summer. If you want to test the later version, is a beta. It's not, so we're yeah, and you can access it directly from GitHub. And so I arrived finally at my conclusions. I have 5 minutes to spare, I hope. So what I tried to show you is that open access standards with Modelica, OpenIPSL can help us address some of the challenges with de facto simulation tools. However, we need to address these social aspects of resistance to change. That's otherwise it's very hard to move forward. So we need actually to convince practitioners, and that's why I wanted to propose this presentation, that we can adopt something better than our existing domain approaches, and that we can actually, you know, always check that we get the correct answer using the existing tool, but we will gain a lot of flexibility and new potential uses for our investment in modeling. And what I think is that regulators should require open access standards and not favor specific software vendors of tools, because there is no competition then. And we're stuck with the same thing since the 1970s. We need innovation in this field to move as fast as, you know, whoever is telling us to have to do all of these things fast, right? We can develop open source models of renewable energy sources, as you see, the same as the ones used by utilities. And we don't have to re-implement them once we have implemented them. And this will be a huge cost reduction and improvement in productivity gains, right? Because now you don't need to wait for the model to be implemented in SIME, in ETAP, in this and the other, and then having to pay them for the new version. So it's a nice way of reuse without loss of information, because instead of exchanging files of parameters, you have the equations, okay? This library is already compatible with 4 tools, and you can use it in 136 tools with the FMI standard. So the ongoing work that we will hopefully have some papers and tools, we have developed a model transformation environment that allows us to read the PSSC models and push out Modelica models automatically. And we have tested that for a model of NIPA that has 500 buses, the model of the Icelandic power network. And so those are, utility scale models. We are hoping to have that ready soon and having the library accessible soon. And of course, I would like to expand the capabilities of the library. So that's the other reason to visit you and participate with you, to see if one of you is interested in supporting this effort. Everything we do ends up being open source and hopefully useful to other people. And with that, thank you for your attention.
Do you have assessment questions?
Yeah, we need the quiz.
We have to test everybody.
And then I'll be around for the questions. I don't know how you do the quiz.
You ask the questions, and we'll have people put them in the chat. The answers in the chat.
I cannot hear you. Can anybody hear me?
I can hear you.
I can hear you.
That's what happens.
Can you hear us?
Let me put on my this.
Okay, can you hear me? Can you hear us? Testing.
Hello.
Everybody, while Luigi is getting ready, I did put in the chat. I did put the link to his PDH of his presentation. So that is in the chat, and we'll keep this open for about 15 minutes, Mark, after we go going, so people can find that and copy it.
Yep.
And Luigi, do you want to ask the questions, and people will type the answers in the chat?
Yes, sure. So the first question is, what is Modelica? And the answers are object-oriented computer and human readable modeling language, computer language that allows modeling inside a physical system, a simulation tool, a library of models. So those are the options. Second question is, what is OpenIPSL? First option is an open source model library built with the Modelica language and compatible with 4 Modelica tools. Option B is a software tool. Option C is a programming language, and option D is a modeling language.
So why don't we go through the answers too as we go through the questions? So what is the correct answer to number 1?
Yeah, so the number 1, I want to look at the answer.
Oh, okay. You have all the answers in one. Okay.
Let me see. I wanted to do answers at 1. Yeah. The third
Okay, go
is
ahead.
what,
Go ahead. We'll keep going. Do it your way.
Okay. The third is, what is the FMI? And there is an option, is that standard for model exchange and co-simulation supported by 100 tools, simulation tool, a programming language, and a modeling language. Point number 4 is, what do Modelica and FMI have in common? The idea is that you would give one example, so whatever you want is fine. And name one of the major caveats of the existing tools. So should I wait or you go through the answers?
Let's go through the answers.
Okay, so in this case, you have 2 answers that are valid because it's both the first one and the second one. It's also a computer language, but not just that. It's not a software tool, and it's not a library of models. Modelica itself is just a language. So these 2 first ones would apply. The second one is, what is OpenIPSL? And this is just a model library built with Modelica, with 4 Modelica tools. The third one is, what is FMI? And this is an open access standard for model exchange and co-simulation, supported by more than 100 tools. Then the idea is that you have an answer, right? What do Modelica and FMI have in common? Well, that they help with model portability with the different simulation tools, and they are both developed by the Modelica Association. And question number 5 is that which caveats are affecting the, well, what are the caveats of the status quo? Is that we can have major design flaws that slam the adoption of new technologies due to the ambiguity of the models and limitations of the tools. And the second one is that implementation or implementation is very costly and time consuming. So those were the questions.
Okay, now we have, basically, I think I can summarize the questions that we had in the Q&A. And one of them, one common theme is about cybersecurity and reluctance to share modeling information. Is there any issue with that, with this, if it's offline or online? How does that affect the development and use?
If you look at so there's different levels to answer this question, right? So, so I work with Dominion. I'm not giving you their parameter values, right? I'm not telling you what they are. So when it comes to the parameter data, you can completely obfuscate that if you don't want to share it. When it comes to the equations, you can always see them. However, if you don't want another person to see it, but you want the computer to be able to understand them, there is means for encryption. So you could hide from your competitor what the equations are, but they're still on the computer can still understand them and process them. So you don't lose the value of having the intellectual property there. So that's the third one. Cybersecurity, you know, it's really a matter of how you do this model management. If you look at the models implemented in all of the tools, they're all online. You can find there, type PSSC, WECC, GenSal. You'll find a PDF with all of the equations. So there's not really a problem with that. I think the question is really, you have all of these parameter files that define the models used by a utility and whether or not that should be shared while they're in the open. That might not be necessary, right? That might be a problem for, you know, you have a consultancy company like deal with it, right? To convert the model if you don't want to do it yourself, or use the tool that we're building to do it, to automate the process. So, I mean, also it's a sad excuse. Cybersecurity comes as a sad excuse. I was working in Europe for 7 years, and I saw there, after a huge effort of 10 years, now they have 52 companies sender their models and solving an entire power flow for the entire for Europe. That's just only power flow, right? This is not all of these dynamic equations, which is now part of the SIM standard because I got it in. So Modelica is part of SIM also. But the challenge is that the way that we've done things here, and we make excuses not to try to work collaboratively. And the reality is that if we keep doing that, we're going to have problems. I mean, there's no way around it. You don't build a plane by not integrating all of the models and all the parameters of the different parts together. So when you think about the aerospace area, they have to do that. And there are different, more than 700 companies that do that, right? So there's that's some thoughts, right? I mean, remember, guys, that I'm a professor, so I don't have the problems that you have. I am just trying to propose some solutions, but the reality is that, you know, the people having the real world challenge of dealing with 1970s technology that barely functions, that's the people that is not taking advantage of the newest technology. You can still use a line, but I doubt that you even use your cell phone to make a call, right? So. Okay.
Well, I guess we'll run out of time. So we want to thank you very much for a very interesting presentation. Like I said, I've listed the link in the chat. if people can find it, it's before the answers to the questions start coming in. And hopefully we can have you back for an update or another application next year.
Oh, sure. There was a question about the IP issues related to embedded controls. There's already a standard called FMI that is being developed by Bosch, BMW. Again, you know, they have to do this very fast, less than 5 years development process. So now there is an FMI standard that allows you to do exchange for the embedded equipment and hiding your IP. So you can have your cake and eat it. You just can't do it with 20th generation technology. You have to use 21st generation technology. So this is also by people that have similar use cases, even worse, because we allow people to not have electricity for 3 days. That was my brother in Woodstock, 3 days without electricity. It's not seen by society very good when plane crashes or when Tesla fails with their autonomous vehicles. So in a way, you know, when in power engineering, we only talk, oh, we have all this responsibility and so on, as an excuse not to advance things. But there are other people that can use an excuse are innovating in this field. And we kind of have to look into that if we want to evolve.
Very good. A lot to think about. So
yeah.
Thank you very much. Best of luck with your research and hopefully see you again.